Hi, I'm a member of the Math National Honor Society, and today I'm going to be talking about linear functions. So first, let's discuss what a function is. So a function is a relationship where there is an input and an output. And so as you can see on the left, we have a table with an input and an output. And so this would be like a function table with the inputs and outputs of the function. So the inputs are commonly known as the x variable, and the outputs are commonly known as the y variable. And for each distinct input, there is only one output. And so what this means is that no input can have two different outputs, but this doesn't mean there can't be two same outputs for two different inputs. And so what this means is that in this table, for example, we can't have the input -1 show up twice with two different values as their outputs. So the pattern between these inputs and outputs is what creates different types of functions. And so in this video, we'll be talking about linear functions in particular. And so a special type of function is a one-to-one function. And what this means is that each input and output are unique. So what this means is that each input and each output are only seen once, and there's no repeats in the outputs. And so a linear function is a function when graphed forms a straight line, as we'll see in the forthcoming slides. And so the dependent variable, y, changes a constant amount for every 1 unit increase in the x variable, the independent variable. And so linear functions always have a constant rate of change, and the rate of change is also known as their slope. And so these linear functions can be written in three different forms: the slope-intercept form, which is the most common form, the point-slope form, and then also the standard form. And so you can also convert between these different forms. And so this is the slope-intercept form. So the slope-intercept form is y equals mx plus b, where m is equal to slope, and we'll see in the next examples and the next forms that m always usually represents the slope, and b represents the y-intercept. Hence the name slope-intercept form, because it includes both the slope and the intercept. And the y-intercept is when x is equal to 0. So this is essentially the point where the graph intersects the y-axis. And the y and x variables just represent the y and the x variables that you can substitute in and solve for. The next form is the point-slope form. So the point-slope form is y minus y1 equals m times x minus x1. And m is once again equal to the slope. And so y1, x1 represent a coordinate of a point that lies on the line. And so unlike the slope-intercept form, this point does not necessarily have to be the y-intercept of the line. And so it could just be any point that lies on the line. And so you can see this is where it gets its name from, point-slope form, because from first glance, we can get a point of the coordinates that lie on the line, and then we can also get the slope from this form. And so the next form is the standard form, which is ax plus by equals c. And so a, b, and c in this form are all just constants. They're not necessarily representing anything, and they don't necessarily have any sort of direct significance to the linear function line. They're all just constants that when you plug in the variables, you'll be able to solve for the other variable. So unlike the previous examples, A, B, or C does not necessarily represent the y-intercept, slope, any point on the graph. They're all kind of just constants. And so slope. So as we saw in the previous example, slope is often expressed as the variable m in the linear function equations, and slope is the rate of change of the linear function. So basically it says how much the y increases or decreases for each one increase in the x unit. And slope is the change in y divided by the change in x. And so this is often shown in the equation as y2 minus y1 divided by x2 minus x1, where x1, y1 is one coordinate pair, and then x2, y2 is another coordinate pair. And so this is also known as the rise over the run, because the rise, as you can see in this example, is how much the graph goes up and changes in the vertical direction or the y direction over the run. So how much it changes in the horizontal direction or the x direction. And so as we can see in this example, we have a straight line, which is a linear function graph, and we have one coordinate x1, y1, and we have another coordinate x2, y2. And so as we can see, this vertical line here represents the vertical change, or the change in y, which is y2 minus y1. And so this horizontal line right here, this represents x2 minus x1, or the change in the horizontal direction or the run. And so when you put this change in y over the change in x, you receive the slope. And so as we said, the slope essentially says how much the y changes for each one increase in x. And so what this means is that the higher the slope value, the steeper the graph is, because this means the graph travels more vertically y in the y direction for each one horizontal unit or each x unit. And so a slope of x indicates that there's no change in the vertical direction, so the graph is completely flat. And a negative slope indicates that the graph is pointing in the negative direction. And so as we can see in this example's graph is much less steep than this graph. So that means this graph has a steeper slope than this graph. And so here are just some examples of what we were discussing in the previous slide. So this is what a linear function with a slope of 0 would look like. It's just a completely horizontal line that has the same y value for all x values. And so this means that the y is not changing at all, which is why it has a slope of 0. And a negative slope is shown right here. So the graph points or moves in the negative direction, as opposed to the positive direction shown in these two examples. And so what this means is that the y changes in a negative direction for each increase in the x direction. And so to wrap up our video, let's just end with some practice problems. So here we have two graphs of two different linear functions. And so for each graph, A, find the slope, and then B, find the equation for the line in the slope-intercept form. So please pause the video and then try these questions on your own, and then we'll go over them together. And so now let's go over the answers to these practice problems. So for number 1a, we're just trying to find the slope. And in order to find the slope of a linear function, we need to find two different coordinates that lie on the linear function line. And so for our first coordinate, x1, y1, let's use the coordinate pair 0, 2. And so when we look at our graph, 0, 2 lies on our linear function graph. And so for our second coordinate, x2, y2, we'll use the coordinate pair 3, 4. And so when we look at our graph, we can see that 3, 4 lies exactly on our linear function line. And so the slope is the change in y over the change in x. And so this would be y2 minus y1 over x2 minus x1. And when we plug in our variables, we get 4 minus 2 over 3 minus 0, and then we get 2 over 3. And so that means our slope is equal to 2 over 3. And so we can verify this graphically because we know that 2/3 also represents the rise over the run. And so this means that for every 2 units the graph rises, it's going to run 3 units to the right. And so as we see in our graph, it indeed does rise 2 units and then run 3 units. And so for part 1b, we're trying to find the equation of the linear function in slope-intercept form. And so slope-intercept form is y equals mx plus b, and we already know m is equal to 2/3 because as we found in part 1a, the slope is equal to 2/3. And after we plug that in, we get y equals 2/3 x plus b. And so now we can either plug in a set of coordinates for y and x and then solve for b, or we could just analyze the graph visually and see where the graph intersects the y-axis, which is what we're going to do in this case because we're already given the graph. And so when we look back at the graph, we can see that the graph intersects the y-axis at the point 0, 2. And so that means our b value is equal to 2 because that's the y value at which it intersects the y-axis. And so after we substitute 2 in for b, we get y equals 2/3 x plus 2. And so this is our final equation for the linear function slope-intercept form. And so now for 2a, we're going to do something pretty much identical to 1a. So we need to find two coordinate pairs first. And so in order to do that, we need to look at our graph. And so we'll use the coordinate pairs -1, 5. As we can see, that also lies on the graph. And then 3, 1. And then as we see, it also lies on the graph right here. And the slope, as we said in the previous problem, is just the change in y over the change in x. And in order to find this, we would do y2 minus y1 divided by x2 minus x1. And so when we solve for the slope, we get -4/4, which is -1. And so what this means is that for every 1 increase in x, the graph decreases 1 in the y direction. So essentially that means it rises -1 units and then runs 1 unit. And so we can verify this graphically by looking at our graph and then seeing that it indeed does rise -1 or decrease 1 in the y direction for every time it increases 1 in the x direction or runs 1 unit in the horizontal direction. And so for 2b, we're going to do what we did in 1b, and we're also going to use slope-intercept form. And the slope-intercept form equation is y equals mx plus b. And as we got in the previous equation, m is equal to -1. So after we plug that in, we get y equals -x plus b. And we could, as we discussed in the last problem, plug in a set of coordinate pairs and solve for b. But instead, since we're given the graph, we can just look at the graph and see graphically where the line intersects the y-axis. And as we can see here, this particular function intersects the y-axis at the point 0, 4. And so that means b is equal to 4 because that's the point where the y intersects the y-axis. And so afterwards, we get the equation y equals -x plus 4. And so with those practice problems, we will conclude this video. And so thank you all for watching this video, and I hope you were able to learn something from this video.